Hello everyone. In previous sessions, we have discussed about parametric hypothesis testing. So before going to start the session, I would like to introduce myself. This is Dr. K. Jagannayaki, Professor in MBA Department, Institute of Aeronautical Engineering, Dundigal. So today I am going to discuss about parametric test. So we know the importance of hypothesis test in research analysis. So coming to the test of hypothesis, so any statistician have, so there are so many statisticians, they have developed several types of hypothesis, and also they have tested different kinds of hypothesis in different types of researchers, and these tests also known as the test of significance. For the purpose of testing hypothesis, basically we are going to classify these tests as parametric and non-parametric tests. So parametric test also known as standard test of hypothesis, whereas non-parametric test considered as distribution free test of hypothesis. Coming to parametric test usually assumes certain properties of the parent population from which we draw samples. So these assumptions are: observations come from a normal population, the sample size is large, assumptions about the population parameters like mean, variance, etc. must hold good before parametric test can be used. The important parametric tests are Z-test, T-test, chi-square test, F-test. So these tests are based on the assumption of normality, that is, the source of data considered to be normally distributed. And chi-square test is also used as a test of goodness of fit and also a test of independence, in which case it is a non-parametric test. So chi-square test is considered basically both parametric and non-parametric test. Coming to the first one, Z-test. Z-test is based on the normal probability distribution and is used for judging the significance of several statistical measures, particularly the mean. The relevant test statistic Z is worked out and compared with its critical value at a specified level of significance for judging the significance of the measure concerned, and this is a most frequently used test in research studies. So this test used even when binomial distribution or T distribution is applicable, on the presumption that such a distribution tend to approximate normal distribution as n becomes larger. So only Z-test is applicable in any type of distribution, whether it is T, Z, binomial, chi-square, whatever may be the type of distribution, one can easily apply Z-test. And coming to the applications of Z-test, comparing the mean of a sample to some hypothesized mean for the population in case of large sample, or when the population variance is known. And second application is that it is also used for judging the significance of difference between means of two independent samples in case of large samples, or when population variance is known. It is used for comparing the sample proportion to a theoretical value of population proportion, or for judging the difference in proportions of two independent samples when n happens to be large. This test may be used for judging the significance of median, mode, coefficient of correlation, and several other measures. Then hypothesis testing of means. The mean of the population can be tested presuming different situations, such as the population may be normal or other than normal, it may be finite or infinite, sample size may be large or small, variance of the population may be known or unknown, and the alternative hypothesis may be two-sided or one-sided. So we may consider some of the important situations. The first situation is that population normal, population infinite, sample size may be large or small, but variance of the population is known. HEA, alternative hypothesis, may be one-sided or two-sided. In such a situation, Z-test is used for testing hypothesis of mean, and the test statistic Z is worked out as under: Z is equal to sample mean minus hypothesized population mean divided by standard deviation of population divided by root over n. So using this formula, we can find out test statistic Z. Let us take one example. A sample of 400 male students is found to have a mean height of 67.47 inches. Can it be reasonably regarded as a sample from a large population with mean height of 67.39 inches and standard deviation of 1.30 inches? Tested 5% level of significance. So, taking the null hypothesis that the mean height of the population is equal to 67.39 inches. So, symbolically, we used to define null hypothesis mu h naught is equal to 67.39, and HA we used to define mu h naught is not equal to 67.39 inches. So, we saying that it is a two-tail test. So how can we identify whether it is one tail or two tail? Based on the symbol in the alternative hypothesis, one can decide whether it is one tail test or two tail test. So in this case, it is two tail test. It means that the rejection region is fall on two sides of the normal distribution curve. So given sample mean is 67.47 inches, the standard deviation is 1.30 inches and n is equal to 400 male students. Assuming the population to be normal, we can work out the test statistic Z as under. So substitute the values in the given formula. Z is equal to sample mean minus hypothesized population mean divided by population standard deviation divided by root over n. So we got test statistic Z is equal to 1.231. As HE is two-sided, we shall be applying a two-tail test for determining the rejection region at 5% level of significance, which comes to us under using normal curve area table. So the critical value of Z at 5% level of significance is plus or minus 1.96, plus or minus 1.96. Now compare this plus or minus 1.96 on both sides. So at 5% as it is two side, the level of significance will be plus alpha and minus alpha by 2. So it will be considered 0.025 on both sides, and here it is minus 1.96, whereas here it is plus 1.96. Just to compare the test statistic calculated value with the critical value. So calculated value is 1.231 and critical value is 1.96. So it falls under acceptance region. Hence we have to accept the null hypothesis. So we may conclude that the given sample with a mean height of 67.47 can be regarded to have been taken from a population with a mean of 67.39 inches and standard deviation 1.30 inches at 5% level of significance. That's how we have to test the hypothesis. Then second case is that population normal, population finite, sample size may be large or small, but variance of the population is known. HEA may be one-sided or two-sided. In such a situation, Z-test is used and the test statistic Z is worked out by using the formula. Suppose we are interested in a population of 20 industrial units of the same size, all of which are experiencing excessive labor turnover problems. The past records show that the mean of the distribution of annual turnover is 320 employees with a standard deviation of 75 employees. A sample of 5 of these industrial units is taken at random, which gives a mean of annual turnover as 300 employees. Is the sample mean consistent with the population mean test at 5% level? So here we have taken the null hypothesis as population mean is 320 employees. So we can define null hypothesis mu h naught is equal to 320 and ha mu h naught is not equal to 320. Again, this is also two-tailed test. So substitute the given data in the following formula and we find out this test statistic is minus 0.67. As HA is two-sided in the given question and we shall apply a two-tailed test for determining the rejection reasons at 5% level of significance, which comes to as under using normal curve area table. So the observed value of Z is minus 0.67, which is in the acceptance region since our Z value, critical value of Z is greater than 1.96 and thus H naught is accepted and we may conclude that the sample mean is consistent with population mean, that is the population mean is 320 supported by sample mean. As it is two-tailed test and rejection reason minus 1.96, whereas if you are going to compare this, it is the computed value is minus 0.67. It falls under acceptance reason. That is the reason we have accepted null hypothesis. Then hypothesis testing for differences between means. The null hypothesis for testing of difference between means is generally stated as H naught mu1 is equal to mu2, where mu1 is the population mean of one population and mu2 is population mean of second population, assuming both the populations to be normal populations. So alternative hypothesis may be of not equal or less than or greater than type for testing the hypothesis. There may be different situations when we are examining the significance of difference between two means, but the following may be taken as the usual situations. The first situation is that population variances are known or the samples happen to be large samples. So in this situation, we use z-test for difference in means and the work out the test statistic z as under z is equal to x1 bar minus x2 bar divided by square root of sigma p1 square plus divided by n1 plus sigma p2 square by n square, where sigma p1, sigma p2, they are denoted as the standard deviation of population 1 and standard deviation of population 2, and x1 bar and x2 bar, they are considered as the means of sample 1 and sample 2. And samples happen to be large but presumed to have been drawn from the same population whose variance is known. This is second situation. So here also we can apply z-test. In case of qualitative phenomena, we have data on the basis of presence or absence of an attributes. With such data, the sampling distribution may take the form of binomial probability distribution whose mean would be equal to NP and standard deviation equal to square root of NPQ, where P represents the probability of success, Q represents the probability of failure such that P plus Q is equal to 1 and N denotes the size of the sample. Instead of taking the mean number of successes and standard deviation of the number of successes, we may record the proportion of successes in each sample. If n is large, the binomial distribution tends to become normal distribution, and as such, the proportion testing purposes, we make use of the test statistic Z as under Z is equal to proportionate value minus P divided by root over P into Q by N. For testing of proportion, we formulate HA and H0 and construct rejection reason, presuming normal approximation of the binomial distribution for a predetermined level of significance, and then may judge the significance of the observed sample result. Let us take one example. A sample survey indicates that out of 3,232 births, 1,705 were boys and the rest were girls. Do these figures confirm the hypothesis that the sex ratio is 50:50? Tested 5% level of significance. So initially we have to define the null hypothesis. H0 P is equal to PH0, which is equal to 1 by 2. Whereas alternative hypothesis defined as P is not equal to PH0. Hence, the probability of boy birth is P, which is 1 by 2, and the probability of girl birth is 1 by 2. Considering boy birth as success and the girl birth as failure, we can write as under the proportion of success or P is equal to half and the proportion of failure 1 minus P, which is equal to Q. Again, it is also half. And N is equal to 3,232, which is given in the problem itself. The standard error of proportion of success can be computed by using the formula P into Q by N. So the standard error is 0.0088. Observed sample proportion of success, which is equal to girl birth rate divided by total births, number of births, which is equal to 0.5275. And the test statistic applies Z test, Z is equal to 3.125. Here also, as in the alternative hypothesis, we have not equal to symbol. So it is considered to be two-tailed test, and we shall be applying the two-tailed test for determining the rejection reasons at 5% level, which comes as using normal distribution curve. The value is again Z is equal to plus or minus 1.96. The observed value of Z is 3.125, whereas the computed value is critical value is 1.96. So it falls under rejection reason. So straight away we can reject. So we conclude that the given figures do not confirm that the hypothesis of the sex ratio being 50:50. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.